Well, good morning or afternoon, wherever you may be, and welcome to another Takeo Tuesday. My name's John Barba from Takeo Comfort Solutions, and joining me on the line here are Dave Holdorf and Rick Mayo. So you have a trio of Takeo trainers, which is lots of alliteration for a Tuesday Takeo session, Takeo Tuesday session.
A lot of teeth there.
There you go. So welcome, everybody. Thank you so much for joining us. We do appreciate the gift of your time. Today's topic is hydronic heating options. The heat loss is done, now what? And our man, Dave Holdorf, will be steering the ship for this presentation. Real quickly, just a couple of housekeeping notes for you. First of all, in your handout section, I've got a PDF of the Takeo Wholesale Catalog, which is just a catalog of all Takeo products that are used in residential / light commercial applications. So in your handout section, at your convenience, please go and download that PDF, and you'll find a lot of really useful information in there, not only on products, but on how to size things, etc. There's a lot of good stuff inside there. Secondly, I just want to make sure everybody can knows how to work the solutions here. The expanded control panel, you should be looking up on the right-hand side of your screen, and you should see a little orange arrow. If it's pointing the way it's pointing in the picture here, you should see everything. If it's not, just click on it and it will expand. You have your microphone or your audio section, so you can make sure your speakers are hearing. Your speakers are on so you can hear us. The handout section, of course. And then down at the bottom is the important part. That's where you ask questions. So I would like you, as we got about 144 of you on the line now, with more coming in every second, do me a favor and just type in a hi, hello, how are you? So I know that you know how to do this, because asking questions is going to be very important. If you're watching this on a device like an iPad or an iPhone or an Android or something like that, your screen's going to look a little different. Okay, you have the buttons down at the bottom. First is screen, so you can toggle back and forth between webcams and the presentation. Your audio settings are there as well. And then skip over to the question mark. That's going to be how you type in your questions. So that'll make it real easy for you. So good, it looks like a lot of you folks can hear okay and have figured out how to ask questions. And the last thing before I turn it over to Dave is this: asking questions is going to be very important. It's how we interact with you. So please type in questions as they occur to you. And one of the things we do differently is we're just not going to wait till the end of the presentation to address your questions. As they come up, we'll address them. As we go along, and we'll stay on the line as long as you guys have questions at the end, which we're more than happy to do. So please type them in as you go, and if they're pertinent ones, we'll address right away. Absolutely. The other thing is treat this as you would treat a classroom presentation. The thing about webinars is you can see us, but we can't see you. So we don't know if you're, looking at your phone or going into Facebook or blah, 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 or whatever. Resist that impulse. Grab yourself a pad of paper and a pen and treat this like a classroom exercise and take notes. This session will, of course, be recorded. Tomorrow you will receive an email with a link to that recording, so you can view it as many times as you wish. That's a given. But to get the most out of the next hour, to get the most out of your investment of your time, resist the phone or resist Facebook or resist email or whatever. Take notes and treat it like we're in a classroom together. That'll be the best part. That'll be the best way for you to get the most out of this presentation. That's done. Now, without any further ado, I'm going to turn it over to Dave Holdorf. Dave, take her away, my man.
Excellent. Thank you, John. Thank you, everybody, for joining us. Thank you, Rick, also for joining us too. I know you're out and about. You're not in your normal dig, so he's going to be also manning the con too. So Rick and John are paying attention to the questions, and they will interrupt me as needed. So I am not going to look at the questions today, I promise. I know a lot of times I do, but it's good to have Rick and John pay attention to those questions to interrupt me when needed. So, all right, so today's class, the heat loss is done, and we've done plenty of classes on how to do heat loss and several different ways, doing it by hand and using software and stuff like that. So, but today I want to talk about, you did the heat loss, and now let's apply it to the house itself, not necessarily just to the boiler. We want to talk about the heat emitters, how we're going to deliver the heat into the space itself, and that's what we're going to concentrate on today. So those are the areas I'm focusing on today. So here's our example. All right, this example you have seen from us several times in one form or another, where we had a 10 by 15 room. It's 9-foot ceilings. My indoor design is 70 degrees, outdoor design is 0. We've got 2 outside walls that you can see here, denoted by 3 windows that we have. R19 in the walls, R38 ceiling. We do that whole heat loss. And here's our numbers for just a really quick review. We see the heat loss of the space at 4,526 BTUs per hour. The entire house, 67,879. The rest of the house, and at 72,405. So we're just going to really concentrate on that one room heat loss today, and let's install heat. Let's get heat installed into this space today is the important part. And also what water temperatures we're going to look at too. So the first thing I want to pay attention to is, baseboard heating. All right, regular fin tube emitters that we put in there. How much do you need based upon that heat loss? And it's sometimes a very overlooked number, and we just slap it in there. And will it heat the space? Definitely. But how much is actually needed into that space itself? Well, we go ahead and take a look at these charts, and all the manufacturers are out there. This one happens to be by Slantfin, and all the different manufacturers are going to have different charts here. Things to pay attention to is BTU per foot that you're going to get out of it. They give you 2 charts, actually two rows, showing you 1 gallon a minute and 4 gallons a minute, and they will give you the BTUs per linear foot, also based upon an average water temperature. And this is important to pay attention to, that a lot of these charts is going to be an average unless it says so. So a lot of times, and guys, answer this question: what do you choose for BTUs per linear foot? What's your BTU output? That is usually your number that you have stuck in your head, and ladies too. And I know what I used to do until I really started paying attention to these things. When you look at the charts here and you look at the numbers and the instructions written by manufacturers, and which row do you use? Do you use the 1 gallon a minute, or do you use the 4 gallons a minute? And I'm assuming a bunch of numbers came in, right, John?
Well, 1 anyway.
Okay, all right. So I know, I used to choose around 600, all right, and maybe you were looking at this 180-degree column, but remember, this is an average water temperature, so which means 180 out, 160 back, typically a 20-degree delta. So we should be taking a look at the 170-degree column here. And then which row do you use is either the 1 gallon a minute or the 4 gallon a minute. And when you take a look at the note down here, right at the very end, use 4 gallon per minute ratings only when the flow is known to be equal or greater than 4 gallons a minute. If you don't know what the actual flow is, if you have flow meters and tweaked it and balanced it and know exactly, then you should be using the 1 gallon per minute ratings. So in reality, we should be paying attention to the 510 BTUs per linear foot, 1 gallon a minute with a 170-degree average water temperature chart. So based upon our heat loss that we have in this application, all right, we saw that 10 by 50, whoops. We see the 4526, divide that by 510 BTUs per foot, and that says, hey, we only need 8.9 foot of element. What are we going to put in there? We're going to get a 9-footer, all right, and which is great because we have a 10-foot wall. You got your enclosure on either sides, and this fits in there just right, all right? It doesn't need any more than that. Putting more in there doesn't get you any more comfort into the space itself. The heat loss on a design day calls for 9-footer element, and that is it. All right. So that's all we need for this installation. If this was a new installation, if you were putting in new heat into this space itself, you just need a 9-foot element of fin tube of this slant fin version here, and that's it. You're done. Yes, sir.
There wouldn't be any issues with them using a 10-footer just because maybe the way the manufacturers ship them out, they go from 8 to 10. Wouldn't be, as long as you had space on the wall for 10, it wouldn't be a problem, would it?
As long as you can get the install in there, yeah. If they don't have the 8, if you put an 8-footer in here, yeah, you're going to be a little short. But then also, how much extra did we do into our heat loss? So when we do our heat loss, a lot of times we do know that we've added a little bit of extra in different areas. So, how close is your heat loss to the actual numbers? Could you get away with an 8-footer? Or if you put the 10-foot in, is it going to be exactly 10? Do you have the space to make the turns and put the enclosures on too? So those are things you need to look at. You know, what's the end cap size, dimensions, and things like that. So correct, good answer, good question. Thank you, thank you. Now, what if you had an application where the baseboard was already installed, and you know it's an existing system, and it might be a little oversized, might be a little bit bigger than what you need, okay? Which we find quite often. All right, let's say your existing system, you know, is already installed, and it's not just the 9 or 10 foot of element that you have, but now it's something a lot more like both outside walls are covered, and now we have 25 foot of element. What could you do? Now we did the heat loss. Now you can actually fine tune the system. I wouldn't go taking any element out, definitely not. And this is something I think we should be starting to pay attention to as we start replacing boilers. And we know we're replacing boilers a lot. We're pulling out the cast iron boiler that was there 30, 40 years ago, and we're going to the more efficient, high efficiency style boilers, lower operating temperatures, and when you can get to that 95, 96% efficiency. So take advantage of the extra element that's installed of this 25, maybe you've got 25 feet in there. We're gonna go back to those charts, and we're gonna operate the baseboard at a lower temperature now. Doesn't need to be at 180 degrees. It would need to be at 180 on a design day if you had the 9 feet of baseboard in there. That would be your high starting point. Now, if we have 25 feet in there, let's go back and we come back to these charts. And if you notice, you know, they give us BTU outputs at lower than 180 degrees, all right, or 170 as your average, all the way down to 110 degrees BTU output per linear foot, all right? And they kind of shade this area out because they're saying, you know, this is ideal for our condensing boilers, all right? You want to operate down here to make that boiler get to that 95%, 96% efficiencies, all right? But they also say, you better make sure you know what you're doing. Do your math if you're going to operate down here too, to make sure you have enough heat into the space itself. So we already know we have 25 feet of baseboard. All right, what water temperature do we want to operate at? Well, we could do a little bit of quick reverse engineering, so to speak. All right, so we got to do the math. All right, we take that heat loss again of 4,526 BTUs. We've got 25 feet. We only needed 9. All right, so we've got 12,000, almost 13,000 BTUs available to us at 180 degrees. But if we zoom in and take a look at, you know, the different BTU per foot, all right, 210, 260, 320, which one? We'll pick one, all right, and do the math. All right, so let's say you start at the 120. Take a look at the 120. You take 210 BTUs per foot, multiply that by 25, and hey, there you go. That number is higher than that number. Yes, it's a surplus, but not by a lot. But if you multiply by the 160 BTUs per linear, then we just don't have enough. So we're going to pull from the 120 degree column, which means 130 out, 110 back, and it's going to be more than enough heat in the space. The advantage is our boiler is going to be condensing when it's calling. All right, we don't need it to operate at that high temperature 180. We can make it high operate at 130 on a design day. And I did this in my house. All right, we had replaced the boiler from the cast iron boiler, put in a new high efficiency wall hung boiler, and I operated around 135 because I had so much extra baseboard that was installed in this house in 1967 that it operated just perfectly. And that boiler just condensed and sang all winter long. Now it's all radiant and still operating at the same temperature, believe it or not, on a design day, and operates down lower from there.
Dave, we have a question.
Yes, sir.
That's from Paul Brune. In the example of this room that you were looking at, would you break up the 9 foot of element into 3 sections so there's a bit of element under each window? To me, that sounds like it's one of those things that sounds good in theory, but in practice, probably not. You'd probably pick the worst case heat loss wall, put your element there, and then, you know, that and call it good, I would think. What are your thoughts?
I understand his question. You know, we always say, you know, outside wall with a window, you put baseboard on it. All right. And that helps you with the washing effect that comes off the glass. So I can understand that. You know, you walk up to the glass and it feels cold right there. You put heat in front of it, you throw hot air to shoot up the wall in front of it, it doesn't feel the same. It doesn't feel as cold when you walk in front of that window. So I think you also want to do what's aesthetically pleasing, right? Instead of putting three 3-footers in there, one 9-footer will look probably better in the space itself. But all you need is 9 feet, so they would both work, correct?
Yeah. And the other thing to think about too is when you put in a piece of baseboard, you really do need 2.5 feet of clear space in front of that piece of baseboard to get proper air convection. So if you were to put them in 3 different spots, you're really shrinking the room if you think about it.
That's right. That's right. Awesome. Thank you very much. Thanks for the questions coming in. Greatly appreciate it. So you can see how we can make these just a little bit better. All right, but do you want to go lower? All right, you want to get lower in your in your design water temperature. There is high, or high output baseboard or low temperature baseboard that's out there. And this one here, as you can see, has 2 pipes in it where you can double the flow if you want to, or you can do a supply and return on the same pipe, but you can also see how much more element there is in there, how much more aluminum to pull the BTUs out of the pipe itself and into the air as it comes across that piece of baseboard. So this one here is called Heating Edge. And here you take a look at their average. Now they're showing you average water temperature in BTUs, and they still give you the 1 gallon a minute, 4 gallons a minute, making sure you know what you've got. And if we were to say, take a look at that, 120 degree column, actually I'm sorry, I put that on the wrong box, just like we've done before. So if you take a look at it, you see those BTU outputs on the bottom, very close at around 208 BTUs per linear foot. But if you want to get more BTUs per linear foot out of it, all right, take a look at the top at the 2 supplies parallel, all right, and they give you nice pictures to show you how you're going to pipe it in there at 385 BTUs per linear foot at 120 with a 130 supply. I'm sorry, this is the proper 130 supply, 110 return, and you're getting 385 BTUs per linear foot. So we could actually drop that down, all right, to say 110 degree column at the 120 if you wanted to get that boiler to condense even more in there. So just a lot of options that you can get away with in covering the heat loads of different rooms. All good?
All good.
All good. Excellent. So great little product here that you can get away with. A lot of heat out of a small package, there. And last but not least, let's take a look at radiant floor heating. All right, and what you can get out of a radiant system here. So now you've got your choice, and instead of how much PEX do you need to put in there? Because we're going through the math to figure out what size everything is. Well, it is also going to depend upon your applications, your installation methods, and things like that. So here's a quick reference chart, and you could find this in a lot of the different manufacturers. They have their installation manuals that will show you your multipliers. And this multiplier is going to be based upon, you take the square footage of the room and what's the spacing of the tubing you want to put in there. If it's a concrete or a mud method or a thin slab, you have flexibility in the spacing itself. If it's a panel system that goes on top of the floor, they'll tell you what that multiplier is going to be based upon what that tube space is already set up in there. Or if you're doing from below the floor, which is 8 inches on center typically with 16-inch on center joist cavities, that's your multiplier. Your square footage of the room times that multiplier is going to tell you how much pipe is going to be needed in that space itself. So we take our room, all right, we see 150 square feet, right? And let's say we are going to do an underfloor method. So we take 8 inches on center, multiply it by 1.5, we get 225 feet of pipe of PEX is needed in that space. Now, if you're doing a slab method, all right, an in slab, whether it's a thin pour or a thick pour, let's say we do 9 inches on center, we multiply that by 1.33 times 150, and we get 200 feet of pipe. If you're doing 12 inches on center, well, we need 100, basically it's 1 square foot of pipe per square foot of room, 1 linear foot of pipe per square foot of room, or 150 feet of pipe. So you get that flexibility. When it comes to radiant floors, how much pipe you put into a space doesn't get you more heat. it gets you different water temperatures. And we'll take a look at the charts if you were to pack in more pipe into a space, all that does is lower your water temperatures. And again, a lot of your manufacturers have different charts out there available for you to take a look at that. And we'll show you one of them today. Now, there are some rules of thumb on maximum loop lengths. It's also going to be based upon your pipe size that you have there, which one you're going to use, whether it's going to be a 5/16 pipe, 3/8, ½ inch, 5/8, 3/4. Usually it's the 5/16, 3/8, ½ inch is most common residentially. Then we go larger for snow melt and commercial applications. But if you're 3/8 tubing, it's around 200 to 300 footers. There's a lot of variables that come into play there. You got to do the math. ½ inch, 250s to 350 footers. And I'm going to work with today, we're going to do some underfloor. I like to use 3/8 for an underfloor, very flexible pipe. You don't run into too many issues and ease of installation. No difference in heat output from one pipe to the other, because it's not the pipe that's heating the space. All right, it's the floor that's heating the space. You're just using the pipe to deliver the heat into the floor, which then heats the space itself. So you don't see any real appreciable differences in pipe size. It's usually the overall loop length, circulator, and head losses and whatnot. All right, so let's take a look at the numbers. All right, you got liters in here too. All right, so we just calculated how much pipe was going to fit in the space itself. Now we need to figure out how much pipe it's going to get from that space to where the manifold is going to end up. All right, so that's your liter length in there. And let's say we're 25 feet away. All right, might be downstairs in the basement where you're going to put that manifold. Could be a central location someplace in the house, but it's 25 feet away, which means 25 feet there and 25 feet back is something that we got to look for. So that's going to be a total of 50 feet of liters that you need to add to your total length in there. So we saw at our 8 inches on center, we had 225 feet of pipe that was needed. All right, and we're going to divide that by 2. All right, that tells us, because we were kind of close on that. We said the 3/8 pipe between 200 and 300 feet. All right, if I didn't add the liters on there, we might be a little on the high side. I'm going to be a little on the safe side here. So divide that by 2 to make it 2 loops in this space. So it's 113. Then add the 50 footers on there. So you end up with 2 163 footers. Yes, it seems very short for the space itself, or you might have one that's really long. That could be a challenge to deal with when it comes to flow and head calculations. So our example that I'm working with today, we're going to say we've got 2 163 foot loops going in that space. Now, the next thing that we like to do when it comes to radiant floor design is find the BTUs per square foot. What's your heat output? We did the heat loss, all right? And the heat loss is always important, even radiant flooring systems, all right? But now we need to find what when we talk about heat delivery in a radiant system, it's how many BTUs per square foot do I get out of it? So it's a real simple equation here. Not a lot of math involved. We're going to take the heat loss of the room and divide it by the square footage. All right, and once we do that, we see here 4526 divided by 150 square feet, and we come in and just round it up, and we come to 30 BTUs a square. All right, so we need 30 BTUs per square foot in order to heat this space. All right, so very, very, very simple math. And when you go through the charts from a lot of the manufacturers, they will always talk about BTUs per square foot. So here I grabbed the chart from Uponor, all right, and here is our concrete slab. Let's figure out what water temperature we need. One of the other things you need to know is also what floor covering is going into the space today. And for the applications when you need to know what floor covering it is. We're going to keep it very simple today, whether it's a tile or close to a low R value wood floor system, or maybe a panel style system that you're putting down. So what is the R value of that floor is important. What you see here on this chart are the different floor covering R values. You've got your BTUs per square foot over here on the left-hand side. And then across the bottom, you'll see your water temperature requirements, what supply water temperature you're sending out to it. and then what differential do you want to operate that at? All right, whether you want to operate a 10-degree differential or a 20-degree. Residentially, you like to do a 20-degree differential, which means if it goes out at 120, it comes back at 110. And that is to give you nice, even surface temperatures in the space itself. If we were to do a wider differential, one side of the room, the floor itself, could feel warmer than the other side of the space. All right, when we go too wide of a differential. Commercial applications will do that all the time, because our concern in a commercial application is not making warm floors. What we want in a commercial application is to heat the building and as efficiently as possible. In a residential setting, what we want is nice, even surface temperatures in the space itself. So we're going to tighten up that delta T, and we can widen it for commercial. I hope that makes sense to everybody. So what you do here is you take a look at your BTUs per square and your floor covering R value, and you're going to draw a line from your BTUs per square foot. Now, this application is also a 9-inch on center. There are different charts for different slab thicknesses that you have. And we take our line and draw it out perpendicular on the, horizontal is what I meant to say, until you get to your floor covering R value. All right. And then we draw a line coming down from the R value that you have for your floor. And where the two lines intersect, we'll bring that down. And for this example, with an R value of say 1.2, you'll have about 125-degree water temperature going out to this slab. If we had just say thin tile would be way back here, maybe at an R value of 0.2, and we can draw that line down, and it's going to hit right here on the 100 line. All right. So when we just, it's the R values are going to right now denote what water temperature. It starts off with the heat loss is going to tell you what water temperature you need, and then what floor covering do you put on top is going to add to that R value. So this is for your slab application. If we go from below the floor, and this one here is showing us joist track, which is a metal plate underneath the floor, where then we snap the pipe up tight into the plates themselves and then insulate behind it. We are going to see, again, the same BTUs per square foot over here on the right-hand side. You've got your floor covering R values. Now, one of the things I'd like to point out here too is this floor covering R value already has a 3/4 inch subfloor built in, because the assumption is all your floors, if you're working your radiant from below, there's already a plywood deck there. And then you put flooring on top of that, and that will be a variable, but the 3/4 inch is already going to be there. So these, make sure you pay attention to that when you look at these numbers, that you already have that 3/4 inch plywood subfloor R value included in here. So here we need to subtract that out from before. All right, so 30 BTUs a square, we subtract out that extra thickness of the R value of the plywood deck. All right, and where the two lines intersect underneath the system, we're going to run, say, around 130 degrees. And I know this conversation comes up quite often, which is better, above or below? And my answer is yes. Don't change the house to fit the radiant, change the radiant to fit the house. It depends on what's going on, how the house is being constructed there. We're looking at a 5-degree difference in water temperature. Not a huge difference in water temperature between above or below the floors. Any questions there, JB?
No, we're cruising along quite nicely here. Thank you. Harry Mosley asked, can I get these charts? These charts are available from every radiant manufacturer has similar charts for radiant floor heating design. So whomever your radiant floor heating supplier of preference is, contact them. They'll have their own design manuals, and they'll have their charts available for you. It's best to work with, pick the company you like and run with it, and run with their design criteria.
Right, and a lot of the manufacturers will also have software too, where you already plug in the numbers and it gets spit out. This is going the hand method. I always like to learn how to do it by hand before I use the software, because the software is just a glorified calculator. And if you don't put the right numbers in there, you're going to trust the numbers that get spit out. So if you know what the numbers are when you put them in, then when they get spit out to you, you know how to work with them, you know how to adjust them. If you had, let's say you had an application here where your water temperatures end up being very excessive, like you see here on the bottom here, it says max design water temperature of 165 degrees below the floor. But you had a really thick carpet and pad thrown in here, all right? And it comes all the way out, and you slide all the way down to say you're hitting that 170, 175 degree water. What do? Well, this is the beauty of our job. One of the things that I would, if this house was under construction, this is new construction, and you're working off a set of blueprints and you come up to say 170 degree design water temperature for this space, well, I would go ahead and lower the heat loss. And not just random willy-nilly at doing it. Go back to the architect or the homeowners and suggest, let's find ways that we can lower this heat loss so I can make the radiant work in here. So yes, will it add more dollars to the construction cost? Yes, it will. All right. Or cost more in heating the space that has, that not as efficient. So can we change the insulation from an R19 to maybe a blown-in style insulation? Or change the R value of the windows, or put smaller windows into the space itself. So if we change some of those numbers, or if you're way out here on this high R value of say R2.5, all right, you probably don't want to put that thick carpet and thick pad down on top of a radiant system. So and that's where you might get into those high R value numbers. Change the carpeting too. All right, make that suggestion. Just don't say, all right, well, that's what it is. We can make that suggestion and make the system work better. So get rid of the carpet for one, but two, if the carpet's not even in there and you're at that high temperature level, then I would look at maybe lowering the heat loss and getting the numbers to a more manageable number.
And you can also look at supplemental heat as well, whether adding some radiator space in with radiant walls or radiant ceiling, or some sort of extra convector, so you don't need to get 30 BTUs out of the floor. Maybe you only get 20 and you make up the difference with whatever supplemental heat there is.
Right. Actually, Olfat had brought up a point. She was talking about considering radiant wall, and wanted to know if you were going to be covering that, Dave.
Actually, a lot of these charts can be applied to the radiant walls too. I don't have much covering into it. You could do it. Basically what you're doing is increasing the square footage of the space. So if you were to do the radiant floor and then go up into the wall itself, you're just increasing your square foot availability, which means your BTUs per square foot goes down because you take that into account. I would maybe do them a little bit separately. Radiant walls does become I think any supplemental that you put into a space is also more added cost that you need to heat that space with. If you were to lower the R value and lower the heat loss of the space, you'll be paying less for the life of the home to heat the space too. So, but no, I wasn't going over. Yes.
I don't think she was talking about supplemental. I think she was just saying, hey, if you were going to cover heating the space with just the radiant wall.
Oh, okay. No, not today. Not today.
Okay.
I didn't want to spend, radiant, yes, we can spend days upon days doing radiant designs. And the three of us here have done a lot of radiant classes over the years ourselves too. So, but not in today's class.
Maybe the short answer to that is find a chart for radiant ceiling heat on how to design radiant ceiling and use that for radiant wall. It's essentially the same thing, only instead of being horizontal, it's vertical. Other than that, it's essentially the same math. Okay.
Right.
And a couple other questions that came up here about well, why did you drop the R value back from the flooring value used before at 1.3? I think there was a question about that, and another question about if a building has tile but also some carpet and others have floating laminate, how do you resolve that? I think the answer there is you design for each one and then you manage your water temperatures accordingly.
Right.
Zone it accordingly. Yeah.
Zoning it is really the best answer there.
Yep.
Right. And yeah, when it comes to why I dropped the R value for this application, because this is the joist heating below floor, which already has the R value of a plywood deck. And You know, the chart before, I had arbitrarily just grabbed an R value. And so I started just grabbing an R value here, and then I subtracted out the 3/4 inch plywood R value for the next chart. So this way I could have similar numbers. I hope that makes sense to you. So this one here, I just grabbed an arbitrarily number. And this one here, I had to subtract out for the 3/4 inch floor. I hope that makes sense for you there. When it comes to different floor coverings, yes, today, we're focusing on one room, just doing the one room itself. If you have rooms with different floors, then you do the same, you always do a heat load design and a radiant design on a room by room by room basis. And you're going to come up with a bunch of different water temperatures easily, because each room has a different heat loss. Each room may have a different floor covering. Your water temperatures are going to become different. You can start grouping some of them together depending upon the spread of design. If you get one room that's 130 and another room that's 127, well, guess what? The room that gets the 127 is going to get 130 degrees. All right, you can group those two together because the water temperatures are close. If you had one room at 100, another room at 130, then you're probably not going to group them together. And as Rick and John were saying before, add more zones to an application. A different thermostat, because the heat load BTUs per square foot may be different. So there's a lot of variables that come into play when you start grouping rooms together based on water temperature also.
And that should answer Mark's question.
Excellent.
He just threw one in there, was pretty much the same. So I think you just answered it.
Okay. All right. As we are coming to, we've picked our different installation methods here. What about the flow rate? What's our, let's size our circulators for it. Let's make sure we got the proper flows, proper head loss, and circulator selection when we come here. And again, this is just one room by itself right now. And let's take a look at the fin tube baseboard application. And we're going to visit our old friend, the universal hydronics formula. We've done plenty of classes with this formula here, where it states GPM equals BTUH divided by delta T times 500. GPM, that's our gallons per minute. That's what we're looking for. Our BTUH, that's the heat loss of the space. All right, that's our heat loss of the space. The delta T is our design temperature drop. In today's example, we've got a couple of different ones based upon the fin tube baseboard or radiant floor. And then our 500 is our universal correction factor that we have in there that changes our constants that we have. So let's plug in the numbers that we know. All right, the heat loss at 4526, 20 degree delta, since we're going to use fin tube baseboard, times 500. So we get the 4526 divided by 10,000. And our flow rate here, just for this room alone, is just under a half a gallon a minute. It's just 0.45 GPM is the flow rate just for that zone. Okay, or if that was to be a zone all by itself. If we have our radiant section, again, we're going to bring out the universal hydronics formula, plug in the numbers that we know. We know the 4526, the heat loss is the same, but now we're going to design it on a 10 degree delta. All right, 10 degree temp drop going there and back to the space itself. So we take 4526, divide that by 5,000, and we get a flow rate of 0.9 gallons a minute, which makes sense, right? We need to move twice as much water to keep the 10 degree delta compared to a 20 degree delta. However, what did we do with the radiant system? We didn't keep it at one loop. We went to two loops. So we're flowing 0.9 gallons a minute up to the manifold, but then we split it and go to two loops, which means my flow rate's going to be 0.45 gallons a minute. Kind of ironic, right? If you take a look at the flows, all right. It's all math. It all comes back and pays attention to it that way. So that's our flow rate. That's what we're looking for in a radiant system, because it's split into two loops. So very low flows. All right. Radiant is always looking for a very low flow rate. And right now our baseboard is, but depending on how we would pipe it in, we probably wouldn't put this room by itself. We would maybe add it to other rooms on a zone. But if it's by itself, we don't need a lot of pump. We do not need a lot of circulator in order to move half a gallon a minute. But now let's take a look at the head loss of our system. And we're going to take a look at the copper, and for our fin tube baseboard application, we're going to run it in copper up to that zone. And in order to figure out our head loss there, we're going to use a quick method today. And our quick method is going to give us a little bit of extra. It's going to be based upon the length of pipe. All right, so we want to estimate the run of tubing of pipe to get there from the mechanical room, from the circulator, measure how much it took to get there, as well as the baseboard itself, and then coming back. Then we multiply that by 1.5, which means we're not going to go through the system, go through the house and count how many elbows are in there, or isolation valves might be in there, or a check valve. We're just going to multiply this by 1.5 to account for all the unforeseens that we're not going to spend a lot of extra time on. So yes, it's going to give us a bit on the high side, but it's going to give us on the high side, on the safe side. And then we may take that number and multiply it by 0.04. And what the 0.04 represents is 4 foot of head loss per 12 inches of pipe running maximum flow for that pipe size. All right, and based upon our estimates of 3/4 inch pipe at 4 gallons a minute, all right, is 12 inches long, we'll have 0.04 foot of head. All right, 1 inch pipe running 9 gallons a minute, also 12 inches long, will also have 0.04 foot of head. All right, so let's do our example and let's find our head loss. And we take that room 1 and we had 50 feet of copper to get there. Okay, there and back, right? 25 there, 25 back. All right, 9 foot of element in the space itself. So we have 59 feet of pipe. Multiply that by 1.5, we have 88.5 feet of equivalent length of pipe. Multiply that by 0.04, and my head loss comes in at 3.5 foot of head. All right, so our requirements for circulator size is 0.45 gallons a minute at 3.5 foot of head. Very, very small. All right, we're looking at really small for our circulator. Now let's go ahead and apply that to our radiant side. And this chart happens to come from Viga, and their tubing, their chart shows us things a little bit different. Now we want to see what the head loss for PEX is. And here you see flow rates in gallons per minute on the left-hand side. And across the bottom here is pressure drop, and this one happens to be 100% water, and foot of head per foot of tubing. All right, is what we're seeing. And then we also see different pipe sizes on the lines that are going from right to left, what tubing size you're using, what PEX size you're using, and then the lines going from left to right here is looking at velocity. So we know our flow rate. We looked at, just under 1/2 gallon a minute, and I'm just going to use the 1/2 gallon line because it was just easier to see. We're going to find our PEX that we're using, and let's say we're using 1/2 inch tubing on this application. And where the two lines intersect, we come down to here, and then we drop a line straight down, and we're going to do some estimating. And this is going to be a pretty easy estimate on what the pressure drop per foot is. If we look all the way to the left at 0.01, and then we go to the next line that says 0.02, our best guess in pressure drop per foot of pipe is going to be 0.015. All right, I think we could all do that there and still pretty safe. We're not going to worry about having incorrect numbers thrown into our calculations here. So let's take a look at the head loss for room number 1 with radiant, and we see that we have a 163 foot loop. Now remember, these are 2 loops in parallel with each other, running out of the manifold. We're not running in series. So it just has to be the head loss for the longest loop. And since they're both the same, the head loss is just going to be per loop. We're not going to add it back up together. All right, we don't have to add that together. GPM is cumulative, head loss is not. All right, so we find our head loss per foot of 0.015, multiply that by our 163 feet of pipe, and the head loss through the PEX itself is 2.4 foot ahead. Now there may be, other head losses involved with manifold and the pipe to get there and things like that. So we're just going to look at what it is in the space itself here. All right. So if you were to take a look at your circulator sizing, and I'm sure most of you have already agree with me that we're looking at very, very low head loss. We're not looking at a lot of head loss here. Your circ demands for room 1, we saw 0.45 gallons a minute at 3.5 foot ahead. So I had plugged up, I turned on my 0018 pump display that I have sitting over here behind me. And to get to where I wanted this circulator to operate at, I couldn't get it to the 0.5 gallon a minute. All right, if you look at our chart here in our zone circulator setting, our gallons per minute is across the bottom, and over here on the left-hand side is our foot ahead. The blue range is where this circulator could actually operate at. But what I was really concerned about where I was setting the circulator up at was making sure that I was able to achieve my over 3.5 foot ahead. So yes, I will over pump this zone. Unfortunately, we don't make a circulator, and I can't dial this one down as low as 0.45 gallons a minute at 3.5 foot ahead. All right, I just couldn't get there. So we're probably we're gonna have a circulator operating at 6.7 watts in order to heat this space. Very, very small, very low power consuming circulator. If you were to put a 007 standard circ in here, AC style, you're gonna be running 80 watts all the time. This is on a design day. Do I need 6.7? So our system curve and might operate way down here, but this is where I would set it up at about 18% speed of the circulator itself. And if we were to take a look at radiant, 0.9 gallons a minute at 2.5 foot ahead. All right. All right. I was trying to probably say, you know what, we're not going to use this as, and most radiant systems, we're going to see zone valves or actuators put onto the manifold themselves. So probably now it's not going to be a zone pump. It might be, we're going to zone valve this system out, and we might see actuators, and actuators are a zone valve. All right. You're just putting, you're just going to control the flow in each zone, and you're going to have multiple loops on that manifold. So you might want to see this circulator, the 0018, in the zone valve mode or the constant pressure mode, where now it's going to slide back and forth. And this was our lowest head zone that we can get out of, lowest head setting that we can get at the circulator at 4 foot ahead, where yes, we needed only the 2.5, so sitting down here, but that's going to get us again pretty close to what we need. 6.9 watts of power, and it would slide up and down as zones opened and closed on this application. Or if it was, you might tie in, if this manifold was going to be by itself, you might tie in a zone valve here and then have other zone valves branched out. So that's usually how I see a lot of radiant systems. As you see, very low flow rates per loop. And we're going to just put multiple manifolds onto one circulator to keep adding, either an inline zone valve or actuators onto the manifold itself. All righty. Any questions?
Oh, we had a couple. One, Joseph asked about where does that 0.04 number come from when estimating head? And that just comes from, it represents 4 feet of head loss for every 100 feet of straight copper pipe at the maximum flow rate for that size of pipe. So for 3/4 inch copper pipe, the maximum flow rate for 3/4 inch copper happens to be 4 gallons per minute. So when we have a 3/4 inch line, we multiply whatever it is by 0.04. We're presuming 4 feet of 4 gallons per minute through that pipeline. If the actual flow rate is lower, the real head loss would be lower, which is why this is a very forgiving and very easy formula. It gives you a lot of fudge factor. But the same number, 0.04, is applicable to all sizes of pipe because we're estimating at the highest flow rate for each size of pipe, which would be 9 gallons a minute for 1 inch, 14 gallons a minute for 1.25 inches, 22 gallons a minute for 1.5 inches, etc. Let's see. Boom, boom, boom. We had a question here from Carrie. Do you have a circulator for each of the 2 loops of PEX? So that would be a no. But can you explain how that? You did explain how that would work, but you could reiterate that for Carrie. That'd be good.
Right. So no, we would look at a manifold, say like this here. Now this manifold is actually showing a 4 loop manifold. But our example today would be a 2-loop manifold. So, and both loops go to the same space. They will both get flow at the same time. It's a parallel header. Here's our zone valve, or this could have been a circulator there, and it would have supplied the flow going out to both loops at the same time. But I would not put a circulator per loop in here. No, that's way overkill. We don't get circulators that small. If anything, you can easily do, say, 10, 12 loop manifolds very easily. The hardest thing about a 12 loop manifold is just getting 24 pieces of PEX coming back to one location in about a length this long. All right, that's usually the most wielding part about it. But flow wise, circulators can easily handle a lot of loops in a house.
Very good. Yeah, and you zone that with manifold actuators, multiple zones on one manifold. So it's essentially a zone valve system, as you said.
Right. Yep. Excellent.
Chris Johnson asks, how are you controlling the supply water temperatures when spaces call for different supply temps? There's a very good question. Very good question, Chris.
Very good question. So if you were to do the heat loss on a house and your water temperatures came relatively close to each other, I would say within 20 degrees from one room to another, then set the boiler for that temperature. All right, especially if you're doing the high efficiency. You've got a high efficiency boiler, you get the flexibility of programming that boiler to do what temperature you want it to do on your design day. So it's going to say, all right, we have an outdoor sensor on this boiler, and we're going to have internal temperature sensors, and you program it to do that temperature that you want it to do. If your water temperatures start to be wildly fluctuating, or we're looking at multiple or different types of heat emitters, maybe we do have a room with baseboard and we have another room with radiant in there. So one's going to be at 180 and the other one's going to be at the 135. Now we're going to use a mixing valve. It's a tempering valve. We're going to lower the water temperature that way, where it uses the 180 coming in, and the return water from the radiant floor is going to blend with the boiler at 180 to get us back down to that 135 degrees. So very good question. I did think about that yesterday to put into this presentation, and it was gone. So
one way to look at this would be, the way I've always done it is, if the three rules of putting different rooms together in a zone are as follows for radiant floor heating, is that the use patterns have to be consistent, meaning the areas have to be used as one. So kitchen, breakfast room, family room, that's all open to one another. Hey, we can put those on one single zone. That's element number one, but all three elements have to be in play. Element number two is the finished floor R values have to be kind of close to one another. I mean, you can't have tile and then heavy, thick carpet and put them on the same zone. That's just not going to work. But you get tile and hardwood with some area rugs thrown in, small area rugs, you're going to be fine. The third element is that the BTU per square foot heat loads have to be kind of close. All right, they have to be kind of close. You put all those things together, the water temperatures required for each area are going to be kind of close. They don't have to be the same. If you got 110, 115, and 125, we can certainly call that good with different types of control, with proper zoning. If you have rooms that have very different use patterns and different water temperatures, what you can do then is pick the highest water temperature you need for that area. So say you got 110, 115, 125, and 135, and it's all the same installation method, right? It's all between the floor joists, let's say. You run 135 to the whole manifold, and then you simply zone each area. So the 110, the room that needs 110 is getting 135, but we're not smoking floors or heating anything because it has its own thermostat. And when it's warm enough, it's going to shut off, and that solves that problem. So that's how you can certainly make that work. My feeling has always been you want one water temperature per installation method. So one water temperature for the slab, one water temperature for between the floor joists, etc. And then make up for the differences in each installation method with proper and aggressive zoning. So that, to me, that's the logical and simplest way to make that problem go away.
Right. So in my own home, I have a 3-temp system. So I have the high temp that the boiler does, and I zoned it separately based upon use pattern, as in The high temperature zone is the apartment that I have on the house, and it's got tall ceilings and hardwood floors. And we're looking at 15-foot ceilings in that space in that apartment. So the heat loss in that space was a little bit higher, and the use patterns were obviously different than my house. So it's actually for my in-laws, and they like it warmer. So the use pattern is they like 74 degrees in the space itself. So that's where we keep it, and it runs off the boiler outdoor modulation. Then I also have radiant slab on my house, which operates at around 105 degrees, and I have a separate mixing valve set up for that. And then the upstairs of my house is all below floor with the plates, and that operates around 120 degrees, and I have a separate mixing valve for that section of the house. So, and again, different use patterns, because the first floor of the house, that's the kitchen, family room, and dinette space. The upstairs of the house is the bedrooms and bathrooms. So everything is used a little bit differently. They're all set up on different zones. Actually, I put every bedroom on it. I went to not just the minimum of, say, 3 zones, right? 3 zones would be one for the in-laws, one for the first floor, and one for the second floor. I also went further and I zoned every bedroom too, just because use patterns. My daughter, who's 18 now, we just got back from looking at schools over the weekend, so she's leaving soon. So what happens in September when she leaves? I don't turn her heat back on. It goes off now. I don't need to heat that space because she's not going to be in there. So, so that's what happens there. When my in-laws go down to Florida in the winter, I keep their heat down low. So now I did a little more aggressive on the zoning too at the same time. So excellent. Thank you. Very good questions. Anything else? Because I have finished my presentation.
No, last call for questions out there, folks. Anything you have, please let us hear about it, because we've got just a few minutes left for our allotted hour. So great time to throw in whatever questions y'all may have at this point. We do appreciate the gift of your time. Hope this has been a useful presentation for you. Dave does a wonderful job on this particular topic. It's a passion of his, as you can tell by how many times he's worked on his own house and has kind of rearranged it. How many times did you rearrange your zoning patterns and setups?
Well, this house was twice, because when I first moved into it, it was all baseboard at first. And I put the new boiler in, and I added the 2 zones, and then I gutted the place to the studs, left the boiler there, and then went radiant throughout this house. My previous home was forced air, and I added radiant to that house also. So, and that one I did as a 3-zone system. So, yeah, I just keep on tweaking and adjusting and messing around it. And especially in the boiler room, I don't like to show off pictures of my boiler room because it is a mad scientist down there. There's lots of valves everywhere, so I can isolate it. And I'm in a closet too, so I had to really jam it into this one space because it's a slab on grade house. So the boiler room is in a closet, and I've got valves everywhere, so I can pull stuff in and out. Working for Taco, we get to try some of the prototype stuff. Sometimes it's a good thing, sometimes it's a bad thing, meaning bad as in, do you want to put something in your house that has never been used before and then travel and not change on it and leave
We're not
the family
traveling anymore.
deal with it? Yeah.
I got a question from another question from Joseph. In the case that you just explained in your house, do you pump each temperature zone separately? Meaning, you have separate circulators for each water temperature, which you would definitely have to have because you have mixing devices, right?
Right. Every time you have a mixing device put into a system, you do need to add a circulator after it. So that's where the flow design is needed on the mixing side of that mixing valve. So I do have 3 circulators for my house. So one for the high temp, and one for the slab, and one for the upstairs of the house. And they're all variable speed circulators there too. So the upstairs part of the house, that has the most aggressive zoning with actuators on that manifold. So that one I have in like the 0018. Actually, I think it is an 18 in there. I can't remember anymore. So I do have the 18 on there in the constant pressure mode, where it is going to change speeds as the actuators, as zones open and close. The downstairs slab is a VDT, one of our older Delta T circulators, and I got my hands on a 006 VDT, very low flow for that area. So that will change speed of the circulator based upon the heat loss, as it gets colder and warmer outside, the temperature changes and the heat demand changes. So that circulator is variable speed. And then the in-laws apartment is a fixed speed circulator at the moment. There is a new circulator sitting right next to it that I want to put in one of these days. I am putting another 18E over there because they have 3 zones in their apartment. So I want to make that circ variable speed. But every time I think about doing it, heating season has started, and you never mess with a system that's working during heating season. You
Right.
have to do it in the summertime. So
Frank Taverna brings up a really good point. Make sure to remind people whenever you have a mixing valve, the circulator for that water temperature is after the mixing valve. Otherwise, it really won't do too much. So you got to get that ready. You got to get that ready. Got to do that the right way. And Jerry Aponte asks, is it common to have a circuit setter in a scenario where you may have a unit heater included with a coil? I'm wondering if that's what he means by I'm not entirely sure what you mean there, Jerry. If you could explain that. Common to have a circuit setter in a scenario where you may have a unit heater included with a coil. I'm wondering if that's
sounds like you got 2 forms of heat in the space there. So you want to balance that heat, and why you have 2 forms of heat in there. Maybe one supplemental to the other. And so if I probably wouldn't need a circuit setter if you had 2 forms of heat, if one is supplemental to the other in the space itself. Like, you're using the unit heater, the heat most of the time, and when it gets really cold out, then we're going to have the fan coil kick in. At that point, no, you wouldn't really need a circuit setter. But if you need them both running at the same time, then you do need to balance it, yes. But if you don't, maybe clarify that too on what you've got going on in your system. But it wouldn't be flowing through. These are going to be 2 separate because they're 2 different types of heat too. So that would be, say, hooked up on a manifold. Could be separate circulators, could be separate zone valves on there, on what you got going. So.
Very good, very good. Can you control the temperature independent? And I think, is there a Takeo controller for that? Asked Tran. I think we're talking about any kind of a motorized mixing valve for water temperature control can be used. Takeo does have one called the I valve. And again, encourage you to download the Takeo wholesale products catalog from your handout section, and you can look up the I valve in there. But yeah, an I valve is just a motorized mixing valve with a built-in outdoor reset control built into the little control head. You just connect an outdoor sensor to it, a strap-on sensor for the water temperature supply, and then you can program it properly. You will have built-in outdoor reset for that one particular water temperature. Always good to use something like that. Even if you have a modulating condensing boiler and you have a multi-temperature, multi-load system, set up the ModCon boiler to do reset and take care of the high water temperature, and then you can use an I valve with reset for your lower water temperature or temperatures if they're multiple, and you reset off of the reset, which is a great way to run a system. That way you can really maximize the efficiency, because when those I valves start resetting, you're sending lower and lower water temperatures back to that boiler, and the boiler loves that.
And that's the exact setup that I have in my house. I do have the I valves operating my 2 lower temperature zones, the slab and the upstairs at my house. So a set point mixing valve is not bad, regular thermostatic style mixing valve. The downside is when you set it for 130, it gives you 130 always. And in a radiant system, and I say this a lot of times and I freak people out, there haven't been too many customers out there that have ever asked for a radiant floor heating system. All right, and you have to stop and think about that for a second. Nobody has ever asked specifically for radiant floor heating. If they say those words, what they're really asking you for is warm floors. And when do you want warm floors? Always. Whenever my feet touch the floor, that's when I want it to be warm. So if you have a set point thermostatic mixing valve, and it sends, and we do our design like we showed today. Remember, all our design stuff was based upon design days. It's 0 outside. 0 degrees outside, I need 130. When it's 50 degrees outside, we need heat. We just don't need as much. So imagine when it's 50 degrees out, yeah, you still want some heat in that space. I still want my floors to be warm. And thermostat calls for heat. Pump turns on, starts pumping 130 degrees out to the floors. The floors heat up. Once the floors get heated up, then we start putting heat into the air. Then the air starts to warm up. The thermostat says, hey, dude, I'm done. Shut off. I'm happy now. And then all of a sudden the floor says, so I've got all this extra energy here. I'm going to keep giving it off because I can't keep it. All right. And it starts giving it off into the space itself. And the air temperature in the space starts to climb. Now, meanwhile, the floor at that point is now cooling down as the air temperature's up here, and then the air starts to cool down. And once it gets to set point, what the thermostat's set for, all of a sudden, this could be a couple of hours before it cools down. This whole time, the floor's getting even cooler. And then all of a sudden, we get past set point, click, and the floor kind of wakes up and says, oh, you want me to do some heating again? Okay, hang on a second. This is going to take a little bit. And then now the heat comes back into the floor, slowly heats up the floor again till it gets to, oh, now I can heat into the air. All right. And then we do this big cycle again. This big flywheel happens to occur. And so now all of a sudden homeowners start experiencing saying, you know, the radiant's not everything I thought it was. I get warm floors. I get cool floors. The thermostat is fine. You know, we come over and take a look at the mechanicals and the room is, all the stuff downstairs is doing what it's supposed to do. It turns on, turns off, you know, pump turns on, it's pumpulating, and the mixing valve is mixing, and, you know, it looks great. But that's because, you know, we don't spend our entire winter at zero. So take that thermostatic mix valve out, put in something like the I valve, put the outdoor sensor on, program it, says, all right, when it's 0 out, give me 130. When it's 50 out, give me something less. But I can also have a bottom end on that too. It's a setting on the mixing valve, and say, all right, only send out, say, 95-degree water when it's 50 degrees out. And now we still have that consistent warm floors when the air needs it in the space itself. So whenever looking at radiant, I always try to modulate the water temperature as much as you can, because think what the customer is looking for. Warm floors, not radiant floor heating. Excellent questions. Thank you. And like I said, I wanted to put that in there. So
very good. All right. Terrific. Well, I think that might do it for us. I think we've had a great, a terrific group of guests out there. Thank you so much, folks, for the gift of your time. We thoroughly enjoyed spending this hour with you, and we hope to see you again in the second quarter of this year. We're going to be doing our Taco Tuesday shows weekly, and we will be alternating commercial and wholesale/residential every week, and we'll be doing that just for the second quarter. So make sure you keep your eyes and ears open for that. We'll look forward to having you on those as well.
Yep,
So
we'll
any final words, Dave?
We'll send an email out when we have the schedule all done, and also pay attention to the website. Go to the training portion, pull down, you'll see the Taco Tuesdays, and the topics will show up there. So
very good. All right. Thank you, everybody. Have a wonderful Tuesday and enjoy this beautiful spring weather if you happen to have it where you are, which we do here in New Hampshire. So it's kind of nice. So
excellent. Enjoy. Thank you so much for everybody.
Take care.
See ya.